There are 4 mechanisms that you're going to need to know. One of them is nucleophilic attack, loss of a leaving group, rearrangement, and proton transfer. We'll go through each one of those. We'll start with nucleophilic attack. You'll show mechanisms, which is just showing the electron flow by using arrows. The tail of the arrow must start on a source of electrons, and the head shows where those electrons go. So our first example, we've got bromine ion. This is our nucleophile. We have our arrow, and it starts on a source of electrons. We'll make these electrons blue. These electrons are going to attack this center right here, and they will make this bond right here. These electrons are forming this bond. So here we've got a different example, also a nucleophilic attack. We've got electrons right here that are going to attack this electrophilic center. It's electrophilic because the electron density is being pulled away. We've got a dipole here, also a dipole here. So there's a deficiency of electrons here. It makes it an attractive target. So these electrons attack this carbon right here, and the result is, let me get the right color, this bond. So the electrons here that were a lone pair are now being shared with the carbon and making a bond. So in the first example, we had 1 arrow. In the second example, we had 2 arrows. And here we're also going to have 2 arrows. Here we have the base of our electron is on this pi bond. These electrons right here are the ones that are attacking the sulfur and resulting in this bond right here. Note our arrows go into the sulfur. Sulfur then kicks some electrons out to the oxygen. So we could also, if we wanted to, draw that these electrons that were involved in a pi bond are now lone pairs up here. So what we're showing with our mechanisms is the flow of electrons. We can also have loss of a leaving group. Let me get it down here so I can. So here we've got electrons that are attaching this carbon to this bromine, and they are being transferred to make a lone pair. They end up over here. One of our lone pairs are the electrons that used to be shared, and that leaves this as a deficit. Now that is shown with just 1 arrow. You can have a loss of a leaving group with more arrows. Here we have a set of electrons that come down and make a double bond here. Nitrogen can only have 4 bonds, and so these electrons come down and make this pi bond. Carbon can only have 4 bonds, and so these electrons get kicked down and become these electrons. And finally, we'll do fuchsia. These electrons become a lone pair here. So we're showing the flow of the electrons as they move from atom to atom, or they change how they're bonding. Okay, so that's 2 of the 4 that you're going to need to know. Here's the third, proton transfers. And we've sort of already done this. We talked about acids and bases. We did some proton transfer. We will use 2 arrows for a proton transfer. Protons do not occur in solution like that. So if we have it in an aqueous solution, we'll draw a hydronium. Okay? And we don't just lose protons. They have to go to something. They have to be taken off on something. So here we've got a proton transfer. We start with these electrons right here. And they attack this positive area of a proton. And we end up with these protons, these electrons making, this bond right here. And it's not drawn, but you also end up with a water. Here's another proton transfer. We've got electrons here that attack this proton. These electrons go to the oxygen here. So let's make some different colors. These electrons are going to end up as lone pairs, and these electrons end up making a bond here. Oops, they should be pink. All right. The third mechanism that you're going to need to learn are rearrangements. And for that, we need to talk a little bit about carbocations and how we can increase their stability. First, we have a methyl group, a methyl carbocation. It has no groups attached to it. It's not very stable, and you're not really going to see it. This is a primary carbocation. It has 1 group. It is less stable than a secondary. The secondary has 2 R groups on it, and a tertiary has the 3 R groups. And the tertiary is the most stable, and the molecules will rearrange in order to form tertiary. And the way they do this is they will have a hydride shift. Here we have a secondary carbocation. It's got this carbon right here is attached to a carbon here. It's attached to a carbon here and then to a hydrogen. So it's secondary, so it's not very stable. It would be more stable if we could make it into a tertiary. And so that will happen. This hydrogen from over here will shift, and that will make this have 4 bonds. It'll have the original hydrogen it had and its new hydrogen, and make our carbocation this, which is going to be tertiary. A methyl group, if a proton is not available, a hydrogen is not available, a methyl group can shift. And that's what's happening here. We've got a secondary carbocation, and if the methyl group moves over, we can make a tertiary, and the tertiary is more stable, and so that will occur. So let's read the curved arrows and identify the arrow pushing pattern that's utilized. Okay. This is a good place for you to stop and make sure that you can identify these. All right, so this first one is a hydride shift. If this hydrogen moves here, then we've moved our carbocation to another secondary. So this is secondary, and this is secondary. But what's different about this secondary position is that it is now allylic to this double bond. This secondary position is now allylic, and we'll get resonance. So we get 1, 2, 3. Kind of crooked. So we have a positive charge here. Let's get a different color. This can go here, and we'll get a double bond here and a positive charge here. So that makes this arrangement much more stable. This is a hydride shift. Okay, so the B, let's look at B. Here we have a nucleophile. We've got electrons attacking an electrophile. And so this is a nucleophilic attack. Here we have an electrophile attacking a proton. So, and we've got two arrows. We've got a proton transfer. This proton right here is being transferred from this ring to the water molecule. It appears over here now. So this is a proton transfer. Here we have a nucleophilic attack. We've got electrons, and they're attacking something that's positive. And let's move it up. So we've got some more, one more. And this is loss of a leaving group. We abbreviate leaving group LG. We'll be seeing that a lot because the chlorine is just becoming chloride.